So, good morning, class. So, for today, I'll be discussing Form 121, Basic Calculations in Pharmaceutical Analysis. But before I start, I hope that you have read your notes for this particular part of the module. All right, so let's start. So these are very important calculations that we have to remember. It's because we will be using this one all throughout the semester. So we have different basic pharmaceutical calculations that we have to remember. Some of them were already discussed in our pharmaceutical calculation, like your equation strength and ratio strength together with your dilution of your solution or diluted solutions or diluted concentration. So let's start with the first one. You have the percent strength and ratio strength. So for this one, these are the following formulas that we can make use of. We have the percentage weight by weight, percentage weight by volume, percentage volume by volume. Right? So please remember the following units when you are computing for each different formula using this different formula. So for weight by weight, you can make use of mass of solute divided by mass of solution times 100. So you have to make sure that your solution are similar. So for example, grams with your mass of solute and mass for solution is also or should be in grams. For weight by volume, so mass of solute over volume of solution times 100. So for this one, you have to make sure that your unit are related with each other. So for example, grams and milliliters. And then for volume over volume or volume by volume, so volume of solute over volume of solution times 100. So again, you have to make sure that your units are the same. So for example, milliliters over milliliters. And then for ratio strength, it is between two values, so portion of a whole, wherein the value at the left side is the portion or the part of the solute, and on the right side is the part of your solution. It is separated by a symbol which is your colon, and it is read as is to. So for example, 1 is to 10, 1 is to 20, 1 is to 5. It is related to your fraction. Yung only difference with your fraction is that it is separated by yung symbol that is being used. And yung how we read the fraction, it is over. So for example, 1 over 5 for ratio, it is 1 is to 5. Right? So let's have an example so that we can remember or understand better the percent strength and ratio strength. So for example, this problem, how many grams of dextrose are required to prepare 4,000 ml of 5% solution? So what are our given here? So our given would be you have you have the volume of the solution, which is equivalent to 4,000 ml. You have the percentage weight by volume, which is equivalent to 5%. And what is missing now is the mass of your solute. So what would be our formula? So formula is percent equals mass over mass times 100%. So we are looking for the mass of the solute, this one. So our derived formula now will become percent times mass of solution divided by 100%. So 5% times, sorry, this would be volume of the solution. So this should be volume. So 4,000 ml divided by 100%. So what would be the answer now? It should be 5 times 4,000 divided by 100. Cancel the unit of percentage. So 5 times 4,000 divided by 100 is 200 grams. Alright, so what about the ratio strength class? So for ratio strength, since we already know the mass of the solute, so 200 grams divided by 4,000 ml And then we can assume that 200 grams is one part of the solution. So X part for the total number of parts of the solution. So X equals 4,000 ml times one part divided by 200 grams. Answer would be 4,000 times 1 divided by 200 is 20. So it means you will be using 20 parts or a total of 20 parts for the total solution. The ratio strength now is equivalent to 1 is to 20. So how will you know if your answer is correct? So convert this to percentage. 1 divided by 20 times 100% is equivalent to 5%, which is the percentage of your solution. Alright? So that is now for percent strength and ratio strength. So I hope you can still remember this part from your pharmaceutical calculation. Next would be parts per million. So the same with our percent strength, you will make use of three possible solutions. The only difference lang here is that instead of using or multiplying the equivalent with 100%, we will multiply it with 1 million. So mass over mass of solution times 1 million, mass of solute divided by volume of solution times 1 million, volume of solute over volume of solution times 1 million. So again, what we have to remember here is that we have to always make sure that the units are the same or they are related with each other. As for example, for mass, if the mass of solute is in grams, the mass of solution should be in grams also. For the mass over volume, if the mass is in grams, the volume should be in milliliters. Okay? And then for volume, if the solute is in milliliters, the solution should be in milliliters also. So let's try to have an example problem. So 65 milligram of a drug additive was added to an animal feeds. The total of the prepared feeds with the drug additive was 5.2 kilogram. Compute for the concentration of the drug additive in parts per million. So let's write the given first. What are the given? So you have 65 milligrams. We have the given. So the mass of the solute is 65 milligram. And then the mass of the solution is 5.2 kilograms. And the ppm is what we are trying to determine. So before we determine the parts per million, we have to make sure that your mass of solute and mass of solution have the same unit. So let's try to convert this one into kilograms. So 1,000 milligram, 1 gram. So using dimensional analysis, we can convert milligrams to kilograms. So 1 kilogram is 1,000 grams. Answer would be 65 divided by 1,000 divided by 1,000 or 65 divided by 1 million is equivalent to 6.5 times 10 raised to negative 5 kilogram. Yeah. So can we compute now for the parts per million? Yes. So let's use the formula. ppm is equal to mass ng solute, mass of solution, times 1 times 10 raised to 6. So 6.5 times 10 raised to negative 5 kilogram divided by 5.2 kilogram times 1 times 10 raised to 6 or 1 million. Answer would be 12.5 parts per million. So 12.55 parts per million. So that is now for parts per million. So another solution would be convert 5.2 kilograms to milligrams. You will get the same answer. So 65 divided by 5.2 times 1 million is 5.2 million. So 65 divided by 5.2 million is, you will get also 12.5 parts per million. Times 1 million is 12.5 parts per million. Okay, so that is another solution. Next part, you have the molality, molarity, and you also have the normality. Right? Yeah. So these are very important solution or concentration expression for solution. For molality, it has a symbol of small letter m. So it means it is the moles of kilogram per number of moles per kilogram solvent. So unit for this one is moles per kilogram. Or you can make use of the small letter m or molar. Molarity class is number of moles per liter of solution. The unit for molarity is moles per liter. You have the m or the molar. Another important aspect of molality and molarity is the n. So how do we compute for n? By using this particular formula. Number of moles equals weight of samples in grams. So we have to remember that the weight is always in grams. Then molecular weight is the total atomic weight of the compound or the substance. So for example, water, what is the molecular weight of water? You have hydrogen is equivalent to 1, oxygen is 16. You have 2 atoms of hydrogen, so you have 2 plus 16 is equivalent to 18, and the unit for atomic weight or molecular weight is grams per mole. Alright? So you will just have to get the total of the atomic weight of all the elements in the compound. Together with their atoms, you have to consider the number of atoms. Alright? Yeah. So the difference between molality and normality are the units. So liters for molarity, kilogram of the solvent for molality. Alright? And then next would be you have your normality. So for normality, it is termed as your equivalent per liter. Number of equivalent per liter of solution or number of milliequivalents per liter of solution. So yung mga possible units would be for this one, we have the MEQ. If you will use this formula, we have MEQ per ml. This one you have equivalent per liter. Or you can make use of the symbol capital letter N or the normal. Those are the units. So you have two possible formula for normality. So you have weight of solute over milliequivalent times volume of solution in milliliters. So if you're going to make use of the MEQ, you have to make sure that your volume is in milliliters. And then if you're going to use this one, your volume is in, sorry, this should be in liters po dapat ito. So weight of solute times factor divided by volume of solution times volume of solution in liters. Okay, so for MEQ, we have to make use of these two formulas. We have molecular weight divided by factor times 1000, or MEQ is equivalent weight over 1000. So equivalent weight, its formula is molecular weight divided by factor. So yung factor class is how do we determine the number of factors for a particular substance? We will make use of these three principles. So for acids, it is the number of replaceable hydrogen. For bases, it is the number of replaceable hydroxyl ion. And then for salts, it is the total positive valence. So again, please remember the following principles. Okay? So let's have an example of the mill equivalent. So let's have the factor first. For acids class, for example, for acids, so for acids, so you have hydrochloric acid. How many hydrogen? So you have one. So it means its factor is 1. So I can only donate one hydrogen, or it will only replace one hydrogen. What about sulfuric acid? We have H2SO4. How many hydrogen? You have 2. That's why yung factor would be 2. For a triprotic acid, you have phosphoric acid. So this is a diprotic, your sulfuric. So how many hydrogen? You have 3. That's why the factor is 3. For bases class, it is the number of hydroxyl ion. Yan. So for example, sodium hydroxide, how many hydroxyl ion? You have 1. So the factor is 1. You have magnesium hydroxide, MgOH, open close parenthesis 2. You have 2 hydroxyl ion. That's why its factor is 2. You have aluminum hydroxide. You have 3 hydroxyl ion. That's why you have 3, a factor of 3. So very important class in this part is we have to be familiar with the chemical name of our compounds. Alright? That's for acids and bases. What about for salts? So for salts, it is the positive valence, total positive valence. So for example, sodium chloride, what is the valence of sodium? It's positive 1 and its number of atoms is 1. So 1 times positive 1 is 1. So factor is equivalent to 1. What about sodium carbonate? So what is the valence of sodium? Positive 1. You have 2 atoms of sodium, so 2 times positive 1 is positive 2. So total positive valence is 2. So for potassium chloride, you have positive for potassium, total valence will be 1. So yung factor niya is also 1. Right? So that's for salt. You just have to consider the total positive valence of your salt. For computing for the equivalent weight or the MEQ, so for example, hydrochloric acid, so HCl, its molecular weight is hydrogen is 1, tapos 35.45. So molecular weight is 36.45 plus. So unit is grams per mole. So if you're going to use this formula, you have to determine the equivalent weight first. So equivalent weight is equivalent to the molecular weight, 36.45 grams per mole, divided by the factor, which is yung factor for hydrochloric acid is 1. So 1. So yung equivalent weight is 36.45. And then to determine now the MEQ, so 36, we'll use this formula, equivalent weight divided by 1,000, 45 divided by 1,000. Answer would be 36.45 divided by 1,000 is 0.3645. So 0.03645 MEQ. Alright? That's for the MEQ of your hydrochloric acid using this particular formula. Let's use this formula, the other one, this one. So you should get the same answer. So MEQ is equivalent to its molecular weight, grams per mole, divided by factor times 1,000. So 1. The factor is 1. So 36.45 grams per mole divided by 1 times 1,000. You will also get 0.03645 MEQ. Alright? That's for our MEQ and for the factor. So that's for normality. Let's have an example for computing molality, molarity, and normality so that we can compare the following. So let's have this example. So 5 grams of sodium hydroxide was dissolved in enough water to make a total volume of 250 ml. Compute for molality. So what are our given here? Ano po yung mga given? We have the weight of the sample, which is 5 grams. Volume of the solution is 250 ml. So we can convert this to liters by dividing it with 1 liter per 1,000 milliliters. It's equivalent to 0.250 liters. Okay? And then for the mass of the solvent, it's since water is our solvent, it's 250 solvent. Mass of solution, sorry, is 250 grams. Mass of solvent is you have to subtract total weight of the solution with the weight of your solute. You will have now 245 grams. Convert this to kilograms, it is equivalent to 0.245 kilogram. And then molecular weight of your sodium hydroxide is you have 23 for sodium, so 23 plus 60 plus 1 for hydrogen. You have a total of 40 grams per mole. Okay. So those are the given that we will be using for determining now the molality, molarity, and normality. So let's determine the molality first. So for molality, what is our formula? Small letter N over kilogram ng solvent. So weight, sorry, this should be N. So molarity is equivalent to N over kilogram solvent. So let's substitute. N is 5 grams divided by 40 grams per mole for the molecular weight. And then the kilogram solvent is 0.245 kilogram. So what is the answer? 5 divided by 40 divided by 0.245. You have now 0.51. So cancel the unit of grams. What's left is the mole per kilogram. So the mole is found at the numerator, the kilogram is at the denominator, or M or molal. That is now for molality. Next would be your molarity. What is our formula for molarity? Capital letter M is N over liters of solution or volume of solution in liters. So M equals 5 grams over 40 grams per mole divided by 0.250 liters. 0.250 liters. What would be the answer? So 5 divided by 40 divided by 0.250. Answer is 0.5 moles per liter. So cancel the unit of grams, or you can make use of capital letter M or the molar. Yeah, so that's for molarity. Next would be normality. So there are two possible solutions for molarity. So in your laboratory, you will be using this particular formula. So N equals weight over MEQ times Mn of the solution. The weight is 5 grams. MEQ, its formula is molecular weight divided by factor times 1,000. 1 times 1,000 times 250 times 250 milliliters. So 5 divided by 0.04 times 250, it would be 0.5 MEQ per ml or N or normal. So in the laboratory, normality is very important. It's because we will be using this one in our titration method. So for the concentration, what we make use for titration is your normality. Molarity, on the other hand, is frequently used for determining the pH. Okay? So please remember, molarity is for pH, and for titration, what we commonly use is the normality. Okay? So did you notice? If you notice, your normality and molarity, they have the same answer. So that is true if your factor is equivalent to 1. That means molarity equals normality if the factor is 1. Okay? If you wanted to convert now, what is the relationship of molarity and normality if the factor is more than 2? So if, for example, you want to determine now, you want to convert molarity to normality, your formula would be M times factor. And if you want to convert normality to molarity, you have now N divided by factor. Alright? So again, if the factor is 1, the molarity and normality are equivalent, or they have the same value. If factor is more than 1, if you want to convert molarity to normality, it is molarity times factor. So it means that normality will have a higher concentration if the factor is more than 1. If you want to convert now normality to molarity, you will use this formula. Molarity equals N time the over factor. Alright, so those are simple ways in converting now molarity to normality or vice versa. Alright, that's for normality, molarity, and normality. So next example, what about if you will use now a liquid sample. So, for example, acetic acid. So, 10 ml of acetic acid was added in enough water to make a total volume of 250 ml. So, compute for the molarity, and normality, wherein the density of acetic acid is 1.05 grams per ml. Alright? So, what are the given? So, given would be volume of the solute is 10 ml. So we have to convert this to its weight in grams by using the density formula. So mass equals density times volume. So 10 times 1.05 grams per ml equals 10.5 grams. So cancel the unit of milliliters. What's left is 10.5 grams. And then volume of the solution is 250 also. So the same. If you're going to convert this to liters, it's 0.25 liters. And then for the weight of the solution, so 250 grams is equivalent to 250 ml. To determine now the weight of the solvent, so we have to subtract 250 grams with 10.5 grams. So answer is 239.5 grams. It is equivalent to how many kilograms? So 0.2395 kilograms. Right? What about the molecular weight of your acetic acid? So molecular weight is, its chemical formula is CH3COOH. So you have two carbons, so 12 times 2 is 24, plus 4, it's 28, plus 2 oxygen, 16, 32, a total of 60 grams per mole. Okay? So those are the given. Let's compute for the molality. Molality is in kilogram of solvent. So M equals 10.5 grams divided by 60, 60 grams. So 60 grams per mole divided by the kilogram of the solvent, which is equivalent to 2.395 kilogram. Answer would be, so 10.5 divided by 60 divided by 0.2395. Answer would be, if it's 3 decimal, it is 0.731, cancel the unit of grams, mole or moles per kilogram. It means that in every kilogram of the solvent, it contains 0.73 moles of acetic acid. Right? That's for its interpretation. So that's for molality. Possible units would be M or molal. Yeah. Next would be molarity. So what about for molarity? So the same in liters of solution. So M equals 10.5 grams divided by 60 grams per mole over 0.250 liters. Answer, 10.5 divided by 60 divided by 0.250 is 0.7 or 0.7. 0.700. Cancel the unit of grams, moles per liter, or M or molar. Yeah. So if you notice, molality will have a higher concentration. It's because of the denominator. So because a solution for your molality, it's just the solvent. That's why it will give a higher concentration. So that is now for your molarity. Next would be your normality. So for normality, it is your weight times MEQ times MA. So factor is 1, so CH3 COO. So it will donate one hydrogen only, right? So that's why the factor is 1. So 10.5 grams divided by 60 grams per mole over 1 times 1000. It's for the MEQ, formula of the MEQ, times 250 ml. Right? Answer should also be the same, 0.0700 MEQ per ml, or normality, normal, or the capital letter N. Right? So that is now for your normality. You can make use of the other formula for normality. You should get the same answer, but the unit would be different. So for example, this one. So what is our formula? N equals weight times factor divided by molecular weight times liter of the solution. So you have 10.5 grams. You have times factor 1. The unit for factor is actually equib per mole. You have now molecular weight is 60 grams per mole and 0.250 liters. So cancel the unit of grams, the moles. What's left? It's equib per liter. What would be the answer? It should be similar with our answer a while ago. It should be 0.7. So 10.5 times 1 divided by 60 times 0.2. So 0.0700, or N, or normal. So that is now for normality. So those are important ways or important methods in determining the concentration of your solution. You have molality, molarity, and normality. So molarity are commonly used for determining the pH. So for pH, we always make use of molarity. And then for normality, those are used for titration methods. Next or last part of the discussion will be dilution of solutions. So I think this was introduced in our pharmaceutical calculation before. So this is your C1V1 equals C2V2. So this is an inverse proportion. It means if one part increases, the other part decreases. So for example, if the volume increases, if the volume will increase, the concentration will decrease. Okay? Yeah. So let's have an example so that you can remember or understand the principle behind your dilution of solution using your C1V1 equals C2V2. So 100 ml of 6 molar hydrochloric acid solution was used to prepare a 3 molar hydrochloric acid solution. Compute for the volume of the 3 molar hydrochloric acid solution. How many milliliters of water is needed to prepare the 3 molar hydrochloric acid solution? So what are our given here? So you have now the C1B1. So using the formula C1B1. So C1B1 C2V2. So what is our clue here? C1 will always have the higher concentration since this is our initial concentration, and then V1 is our initial volume, C2 is our final concentration volume, V2 is our final volume. So we have 6 molar or 6M. Our V1 or initial volume is equivalent to 100 ml. And then our final concentration is 3 molar. What's missing is the final volume and the volume of your water. So before we determine the volume of water, we have to determine the final volume of the 3 molar or the final volume of the final concentration. So using our formula, C1V1 equals C2V2. So V2 is missing. We will derive now or come up with the final formula, which is V2 equals C1V1 over C2. So 6M times 100 ml divided by 3M. Answer would be 6 times 100 divided by 3 as 200 ml. So if we're going to dilute 100 ml of 6 molar hydrochloric acid to 3 molar hydrochloric acid, we will prepare a total volume of 200 ml. So how will we determine the volume of water? We will subtract our final volume with our initial volume, which is 100 ml. So the volume of water now is equivalent to 100 ml. Yeah. Okay? So that is now for the volume of the liquid or the volume of the solvent that will be used in preparing now the 3M hydrochloric acid. So that is now for our discussion regarding the basic calculation in pharmaceutical analysis. So thank you and good luck.